Okay, so this is the third lab about the black hole. So obviously, the main focus of this lab is on the gravitational force, which can be represented by Isaac Newton's law of gravitation, which describes how every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. And the purpose of this lab is to apply Newton's law of universal gravitation to analyze a star's orbit around a black hole and use this information to find the mass of the black hole and the initial velocity that a spaceship must have in order to overcome the gravitational force that the black hole and another planet exert on it. So some fundamental principles and concepts that this lab touches upon, obviously Newton's law of universal gravitation, which says F equals G times M1, M2 over R squared times minus R hat, where G is the gravitational constant, and Newton's second law of motion, which is also known as the momentum principle, which says that F net is equal to the change in momentum over some time, and then this can also be translated into the velocity update formula, and then that the magnitude of the net force is equal to the magnitude of the perpendicular net force and the parallel net force, where the parallel net force is equal to the change in magnitude of motion, and the F net perpendicular has to do with the change of direction of motion. So some assumptions that I made was that the only force acting on the planet, star, and the black hole was the gravitational force exerted by other bodies. Like obviously there's probably other forces in the universe present, but we didn't consider those. We just set F net equal to Fg. And since the gravitational force is not constant, Vf is approximately V average here. So we can isolate M in this equation to be M equals dp dt r squared over G times small m. And then just the preview of my results, I calculated the mass to be this number and the initial velocity to be this vector. So the first part involved finding the mass of the black hole. So obviously the system here was the black hole, and the only other surroundings were the star, and these are the initial conditions that I specified here. The mass of the star, the delta T, which is 1 Earth day, which is 86,400 seconds, and then obviously the gravitational constant. So to actually find the mass, I had to apply Newton's second law and the law of gravitation. So here I calculate momentum, and then I calculate dp dt by finding the change in momentum, which is equal to F net on the star by the black hole. And then here we can calculate the parallel component of F net by setting it equal to dp dt times p hat. And then you can isolate and solve for the perpendicular component by using this equation here and saying dp dt perpendicular equals to F net minus dp dt parallel, because the components add up to F net. And then here is just the gravitational law isolated for the mass of the black hole. And then obviously this was over many iterations, so many days. So in order to get one final value of mass, I wanted to calculate the average mass. So I summed up all the masses of the black holes here where I added sum until the end of the loop, and then I divided that sum by the number of masses that were calculated, so the count, so the number of loops, to get the average mass, and the average mass was about 1.067 times 10 to the 34th kilograms, and then these were the values of F net and its components that I found. So part 2 was to find the initial velocity of a ship that also entered the system. So these were the initial conditions. Gravitational constant is the same. The planet's mass was 9 times 10 to the 28 kilogram. The ship's mass was 7 times 10 to the 10 kilograms, and delta T was 1 second. So then the next step was to calculate the net force on the planet and calculate the net force on the ship. So here the system was the planet and the surroundings were the black hole and the spaceship. So here I added up all the gravitational forces that were exerted on the planet by the black hole and the ship, and then finally calculate the net force on the ship now. So I set the system to be the ship and the surroundings to be the black hole and the planet. So here I calculate all the gravitational forces on the ship by the planet and the black hole. So then using those forces that I calculated, I updated the ship and planet's velocity and position after each iteration using Newton's second law. So here's a velocity update formula, here's a position update formula. And then I had 3 conditions to find the initial velocity such that the distance from the black hole to the ship wouldn't be smaller than the radius of the black hole, so that it wouldn't get sucked into the black hole. And then the distance from the ship to the planet wouldn't be smaller than the radius of the planet, so the ship wouldn't crash into the planet. And obviously the ship can't travel faster than the speed of light, which is 3 times 10 to the 8 meters per second. So just by plugging in and testing out different values, I found that this value for initial velocity, 10 to the 7 0 meters per second, worked, and it allowed the ship to be 6.9 times 10 to the 10 meters away from the black hole, so without falling in and without crashing. So for part 1, the runtime was of the lab was not that long, so the mass may not have been as accurate. The simulation obviously does not represent reality, so there were probably other forces besides the gravitational force. And then in part 2, I used trial and error to find the velocity, so it wasn't an exact calculated value, and other velocities probably could have gotten the spaceship closer. So what does this mean? So the difference between the rate of change of momentum and the net force is specified here. So this is how you calculate the rate of change of momentum by dividing it into its parallel and perpendicular components. And then here is the net force divided into its parallel and perpendicular components equals to mass times acceleration. So the difference here is that F net is calculated by multiplying the object's mass by its acceleration, which is the average rate of change of velocity over some time, while dp dt is calculated using the instantaneous rate of change in momentum, which is like a value that has to do with velocity over a very short time span. So it's the difference between average and instantaneous. What initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? So if the ship was in the black hole's orbit, then F net perpendicular of the ship would have had to equal F net perpendicular on the black hole so that they would have been changing direction at the same rate. So in order to achieve this, I would have increased the y component of the ship's initial velocity and maybe decreased the x component a little bit. So I didn't calculate an exact value, but it would have had to do something with this relationship. And that is all. Thank you.